When we last heard from prisoner A, he was trying to estimate his probabilities of being released tomorrow, and he realized that they depended on the probability of a certain unknown parameter x. In fact, his chances are this integral over p of x given the background information, the probability distribution of the parameter x. Now, x is a number between 0 and 1. As we saw before, it turns out that it's the probability that the jailer under a certain circumstance will say the letter B instead of the letter C, but it's a probability of 1 among 2 possible outcomes. And the form of our estimate of the probability was a Bayesian probability distribution of that parameter. Of course, as I commented last time, that parameter itself just happens to be a probability. Now, we discussed last time what you should put in for this probability distribution if you don't know anything at all about the jailer's preferences. Those are priors called non-informative priors. That's a technical term, but it describes it nicely. They're what you're reduced to doing if you have no data about the situation. If you're ever among a group of Bayesians and they're debating in a very heated way what to do about a non-informative prior, my advice is just walk away. That's not the power of Bayesian statistics. What you need is data. Now, in this case, data might be a previous history of what the jailer said, whether he said B or C, given a whole bunch of different sets of prisoners under identical circumstances. I know that doesn't seem likely, but let's bear with it as a toy problem here. So here's what data might look like. It would be a succession, a string of B's or C's that tell on each occasion whether the jailer said B or C in the identical circumstance. And I'll save you the trouble of counting them all up. It turns out we have 35 pieces of data, of which 15 are B's and 20 are C's. And we want to estimate the probability that the jailer will say B. Well, you probably will immediately say, what's wrong with just estimating it in the obvious way? There were 35 times, and he said B 15 times. So the probability that is going to say B, or at least an estimate of it, is something like 15 divided by 35, which is about 0.43. That's not wrong. In fact, it's close to being right. But think about it. Are you saying that the probability is exactly 0.43? That in all cases when you get this data, the probability would be 0.43 and not, for example, 0.42 or 0.44? That's the issue that we're now trying to get at. What is the distribution of possible answers for this parameter x? We're going to hypothesize that these data, the B's and the C's, are what are called independent and identically distributed events. That's something that we're going to use all the time, so we've given it the abbreviation IID, and from now on we'll just say IID. And something like this is called, as we'll discuss later, a Bernoulli trial. A Bernoulli trial, roughly speaking, is a set of independent events, each of which has two different possibilities, but with the constant probability on each trial. Now, as good Bayesians, we need to compute the probability of the data given the parameter. That's, of course, the opposite of what we really want. We want the probability of the parameter, and that's where Bayes' rule is inevitably going to enter. This would be a good time to comment about this deceptively simple concept, the probability of the data given the parameter, because it means different things to a frequentist than it means to a Bayesian, and this would be a good time to understand the differences. We'll actually make use of both concepts in different contexts. A frequentist considers not just the trial that we've seen, but the universe of possible trials and how frequently the exact result that we've seen or an equivalent result would occur in that universe. Now, an important point shared by both the frequentist and the Bayesian is the fact that since the events are by hypothesis IID, independent and identically distributed, it doesn't matter how they're rearranged. The probability of a particular outcome should only depend on how many B's there were and how many C's there were. In fact, the probability of exactly the outcome that we see is simply the product of those independent probabilities, a product of an x for every B and a 1 minus x for every C, and so we get these powers of x and 1 minus x. Now the frequentist considers the number of equivalent arrangements, the number of different ways that you could arrange NB-Bs and NC-Cs, and that of course gives a binomial coefficient, something that you should be familiar with, the number of ways that you can choose k things out of n, that is to say, choosing which positions to put a B in rather than a C. The Bayesian considers only the exact data seen without any rearrangements. It's a simpler world in many ways when you don't have to imagine what the universe of possible data looks like. You can just compute the probability of the data as you see it. So the Bayesian writes that that probability is, we're going to use a proportion sign because the Bayesian always computes the Bayes denominator at the very end, this same probability of the exact data seen. However, the Bayesian must assign a prior to the parameter and multiply the probability of x given the data by that prior on the distribution of x given background information. Now, assigning this prior sounds very onerous, but we've already seen that in a lot of cases you can just take it to be the uniform prior or some other non-informative prior. For the next couple of slides, I'm going to assign the prior the value 1. That is to say that all values of x between 0 and 1 are going to be assumed to be equally likely. Notice that there's no binomial coefficient here for the Bayesian. Now, there's actually two reasons for that. There's a trivial reason, and that is that the binomial coefficient doesn't depend on x. And therefore, if it's a constant with respect to x, the same constant would be in both the numerator and in the Bayes denominator when I compute the integral, and therefore that constant will just cancel out. However, there's a more fundamental philosophical reason that we should not put in a binomial coefficient, and that is this idea that we should consider only the exact data seen and its prior, and not hypothesize about what might have been seen in alternative universes. We're going to return to this issue because if it sounds a little bit dodgy, well, it is in some contexts. We're not always going to be Bayesians. When we get to the topic of goodness of fit, we'll see what a problem that is for Bayesians and how easy it is for frequentists to think about. So the Bayes numerator and denominator here are the probability of x given the data, that proportional thing, and you can see that I've now chosen the prior probability to be 1 here. And the Bayes denominator is just the integral of that numerator over all possible values of x, and that's a definite integral over x, which therefore can be a function only of the letters other than x, the nb and the n minus nb, and it turns out you can do that integral and you get this combination of gamma functions. I hope you've seen gamma functions before somewhere in your life. Gamma functions generalize factorials to have arguments that aren't just the integers. In any case, these are known functions, and we can plot now this probability of x given the data divided by the Bayes denominator and get the actual probability distribution of the parameter x. And here it is. This is our complete set of information given that set of 35 B's and C's on what are possible values of x. You can see that the most likely value of x is somewhere around 0.4. We'll compute it more accurately on the next slide. And you can see that it's not exactly certain what value x has. It could be sort of anywhere in this distribution. There's even a very small chance that it could have a value as big as, say, this. Now, when I said previously you can do that integral, I didn't really mean that you could do the integral. What I really meant was that you can have Mathematica or MATLAB do the integral. And this is going to be a theme throughout these lectures. Don't be afraid of difficult algebra or calculus. That's what computers are for these days. They can do it for you. So I won't go through this in full detail, but the basic idea in Mathematica is you write down the symbolic expression for the numerator. You tell Mathematica to integrate the numerator. X goes from 0 to 1. And then there are some little gotchas like if you don't put generation conditions goes to false, you get some garbage that you may not want to look at. And Mathematica knows about gamma functions and gives you the answer right here. Now we can define an expression which is numerator over denominator, and then we can plot that expression here. And there's the graph that was shown on the previous slide. If you don't like Mathematica, you can do the same symbolic calculation in MATLAB. MATLAB has a symbolic toolbox. It's an add-on. It's actually Maple. That's another symbolic program. And again, I won't go through it, but the lines are almost in one-to-one correspondence between the MATLAB and the Mathematica. So from time to time in this course, I'll be showing you how I do the calculations, the analytic calculations, as it were, in MATLAB or Mathematica. What we've been illustrating here is, of course, called Bernoulli Trials, named after the two Bernoulli brothers who lived in the 1600s, Jacob and Johann Bernoulli. Bernoulli trials are events with two possible outcomes. In our case, they were called B and C. The events are IID, and there's a single parameter x, which is the probability of one or the other outcomes here, B. We already saw that a sufficient statistic, so-called, is a pair of numbers, namely the total number of trials attempted and the number of those which came out B. A sufficient statistic tells you all you need to know about the trials. There's no other information than the sufficient statistic, and we know that's the case here because the ordering of the events doesn't matter since they're IID. So we learned that the probability of a particular result of Bernoulli trials is this combination in the Bayesian sense. And therefore, using Bayes' theorem, the probability of x given the data is proportional to that, but times a prior. We also saw that the uniform prior allows us to compute the Bayes denominator, and it's this set of gamma functions. So what can we do with this machinery? Well, if we have an estimate of the parameter x, we can characterize it in various ways. We might ask, what is its mean or standard error? Or let's first do the mode. That would be the most probable value of the parameter x. We can compute the most probable value, that is to say, the maximum value of this expression, by taking its derivative with respect to x in the usual way and setting that equal to 0. You can almost see how it's going to work, but I'll let you go through the algebra. You don't need Mathematica for it. And you'll find that there's a very simple answer, that x is nb over n. This is called the maximum likelihood answer because it gives the value of the most probable single value of x. And it's in fact, remember, what we intuitively thought the answer ought to be when we first saw the data, 15 over 35. Now that's not the same as asking what's the mean value of our estimate of x. The mean value, which is denoted like this, is the average x weighted by its probability. Well, average for a continuous variable means integral, so we have the integral to 0, 1 dx, and x times its probability. And you can do that integral from these. You might want to use Mathematica for that, and you'll get this combination. Notice that it has an nb over n, and as the number of trials becomes large, these two estimates will agree. This one is nb over n, and this will converge to nb over n. But there's more information in this because this tells us how to make the transition to the case where the data is very sparse and where it's determined by the prior. So for example, we could take the extreme case where we haven't done any trials at all. In that case, n is going to be 0, and nb is also going to be 0, and our estimate of the mean of the parameter is a half. Where did that a half come from? It came from our uniform prior. The mean value of something that's flat between 0 and 1 is a half. So you'll see that the mean estimate knows about the prior in this sense. We could also calculate the variance of our estimate. The variance of anything is the mean of the square minus the square of the mean. I hope you've met that somewhere before. So here we already have the mean up here. We have to compute this new integral, which is the mean of the square, and then subtract the square of the mean. And if you do that algebra, you get this combination of n's. Notice that if we do a very large number of trials so that capital N becomes very large and capital NB, the number of B's, also becomes very large, then there are 2 powers of those N or NB's in the numerator, but there's 3 powers of them in the denominator here. So that as N becomes large, the variance gets smaller and smaller. Our distribution of our knowledge of the parameter x gets narrower and narrower, focusing in on whatever the true value is. This should remind you a little bit of our discussion of the minnows at the end of a previous segment when I asked you how many trials would you have to do to be able to estimate the probability to within some narrow range. And you see here that this kind of a formula would give you a way of doing that. We've picked a uniform prior up to now, but we could ask whether there are any other forms for a prior, functional forms, that would still make it easy for us to do the math. Of course, a prior can be based on your previous knowledge and could be as detailed as you want, but here we're just asking an easier question, a question of convenience. Are there any easy priors to choose? And the answer is yes. Consider this prior. The probability of x given our background information. Suppose we think that it's proportional to some power beta of x and some power alpha of 1 minus x. If these are both positive numbers, beta and alpha, then we'll get a curve that has the same kind of character as the curve we saw previously for our estimate. Namely, it'll start at 0 because x to some positive power beta is 0, and it will end at 0 because 1 minus x also goes to 0. And in between, the location of the peak and also the width of the peak can be set to be whatever we think they ought to be as a prior by appropriately choosing values for alpha and beta. I'll leave it for you as a little exercise to figure out how to do that, how to translate a location and a width into alpha and beta. Well, now if we go back to the formula for the probability of x given the data and include this as the prior, we have what we had previously, now times this non-trivial prior. But look, we just have some additional powers of x that go into the integral here, and we have some additional powers of 1 minus x that go into the integral here. And we can do the same integral as before, or let Mathematica do it, and you'll just get some combination of gamma functions that now have these corrections for alpha and beta. Previously, for the flat prior, that would be equivalent to choosing alpha equals beta equals 0, because then this would be x to the 0 and 1 minus x to the 0, which is just the constant 1. Now we see how a different choice of prior comes into our estimate of the probability distribution of x. Priors that preserve the analytic form of the probability like this have a special name. They're called conjugate priors. There's nothing special about them as probability distributions, except that they're especially convenient. So there are a lot of examples where a Bayesian will choose a conjugate prior, not because that really is known to be exactly the functional form of a prior, but because you only know enough to approximate the prior, and there are conjugate priors that give a good enough approximation to what you already know. And in that context, they can be very useful. Notice that if you start with a conjugate prior, you'll also be able to assimilate new data. What does that mean? That means we had our 35 observations of the jailer, and we've gotten our probability distribution. What if another 50 observations of the same jailer come along? What can we do? Well, we could, of course, go back to square one and just concatenate the data and do the calculation over again. Or we could take the probability distribution that we got out of the first 35, which has this functional form for certain values of alpha and beta, go back and figure out what, and that could simply be the prior for our new estimate, and our new estimate would have this same functional form. So that's the convenience of conjugate priors. And there are conjugate priors for many different probability distributions, not only for this probability distribution that occurs in Bernoulli trials. By the way, if I show a special love of Bernoulli trials, it might be because the Bernoulli brothers are my academic ancestors. Academic ancestors are defined by you know who your PhD thesis advisor was, and you look who his or her thesis advisor was, and you try to trace that back in history to find your academic genealogy. It, of course, has nothing to do with genetic genealogy. And mine goes back through this line here, and it divides at Felix Klein because we learn from the history books that Felix Klein had two PhD advisors, Julius Plücker and Rudolf Lipschitz. On the Plücker side, I go back to Gauss here, and then some people before Gauss who you probably have never heard of. I certainly hadn't. And on the Lipschitz side, we go back through Poisson and Fourier and Lagrange and Euler, and here we get to the Bernoulli brothers, Johann and Jakob. Now, I want you to be impressed, but I in all candor have to tell you this is not a very exclusive club, since Gauss and the Bernoullis each have about 50,000 recorded descendants in the mathematics genealogy database. If you haven't gone and looked at the mathematics genealogy database, it's a lot of fun to go and look. And there are probably many, many times 50,000 who just haven't been recorded. The fundamental achievement of the Bernoulli brothers is, of course, the binomial probability distribution. I'm going to write it out one last time. That's the probability in n trials of seeing n successes, let's say, given that the probability of a success is p, and the fact that we just derived that it's a binomial coefficient times these powers of p and these powers of 1 minus p.